Okay.
Yeah.
I'm Chris, and this is...
I'm Colton, and this is...
I'm Danny, and we are the Cold-Blooded Killers.
Alright.
So here is our GUI. Here I'm going to run through its main functionality and show that it satisfies all the core features, and we will talk about the reach features it has to offer later in the video. So first we can go over here to load normal image, and that'll pop up a window that lets us pick a PNG or JPEG file from our computer that we want to use to hide other images. And then if we click load hidden image, we can pick another image that we want to hide, and then can come over to encryption methods and click on the drop down to reveal a bunch of different algorithms that we can apply to hide the hidden image into the normal image. So if we click one, then it generates a new image that looks the same but actually does store the data of this hidden image, and we can click save encrypted image, and a message pops up saying that it is saved as encrypted image.png. Now we can continue to do this with more images and keep applying different algorithms, and so I will go through and hide all 10 images into this one image. Actually, that's correction, it will be 9. And so I only stored 9 images in here because for the 10th image, I'm going to come and load it, and we are going to actually store it with our own voice. We can record audio and use an algorithm to encrypt that into different audio data that we can then extract this hidden image from. So if I click record audio, hello world, welcome to Steganography.
Hello world, welcome to Steganography.
You can see it recorded for 4 seconds from when I pressed record, and then if I encrypt recorded audio data,
Hello world, welcome to Steganography.
then it's indistinguishable, it's the same waveform, and sounds exactly the same. But now if we come over to recovery method, I can run through and extract all the images that we did hide. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And there you have it.
For odd-even red embedding, we first start by extracting the red channel from the picture. Then, we create a for function that encompasses all of these elements to begin splitting them up. We start this process by using the mod function, taking each element and dividing it by 2. If the result of the mod is equal to 0, which means the original value is 2, we turn that value into a 1, making it odd. If the result of the mod function is equal to 1, which means the original value had to have been 1, we turn that value into a 0, making it even. These small values will make it very easy to hide the hidden image into the original. Now that the red channel has been modified, we use the cat function to concatenate the hidden image into the original starting image. Then, we use image sc to display the new encrypted image. Odd even green and odd even blue work the exact same way, except that we extract the green channel and the blue channel, respectively. For odd even red recovery, it essentially works in the reverse of embedding. We start out with a 400 by 400 zeros matrix. We then extract the red channel and create a for function for all of its elements. By using the mod function, if the result is equal to 1, we place that recovered value in the once zeros matrix. We then use the color map so that the image shows up in grayscale. We then use image sc to show the now recovered image. If the wrong recovery method is selected, this error message will pop up to the user. Even odd green recovery and even odd blue recovery work in similar ways, except for green, we extract the green channel, and blue, we extract the blue channel, but do the same thing.
So for our audio embedding, when we first press record audio, then we create an audio object, and that samples at a rate of 44,000 times a second, and we record it for 4 seconds and assign that data to the object. Then we can extract that data from the object, and so when we go to embed, we can take that data, and wherever there is a corresponding 1 in the flattened image for the first 160,000 samples, wherever there's a 1, we add 100,000th to it. And so for the recovery method, if we go, all we do is just compare the original data to the encrypted audio data, subtract it, and then rescale by that 100,000, and we will recover our matrix of zeros and ones.
So our binary embedding method is pretty straightforward. We first take our encrypted data, the red, green, or blue channels, whichever one we want, and we're going to convert all those pixel values into binary. The desc2bind function allows us to convert it into a string array. That way we can convert our flattened image into a string as well. Then we can go through and replace whichever position in binary that we want with our flattened image. We can then reshape it back into 400 by 400 and put it back together. Now it'll be an RGB image that we can display. The recovery technique for the binary encryption is very similar. We just extract the encrypted data, the red, green, or blue channels, and convert them into a character array. So then we can extract the position that we hid in our image earlier. Once we do that, we can convert it back into a numeric and reshape it into 400 by 400 and display it on screen as such. And here it is in greater detail.
And I didn't even but basically, yeah, what it is doing is the function goes through, takes the red, blue, or green channel of the dog image, and it converts it. It takes the 400 by 400 array and flattens it so that it is 1 by 1,600 or 160,000, and then converts it into binary. But the MATLAB function desc2bind converts it to binary strings. So we go and take our flattened image of the flattened image of our hidden picture that we want to hide. That is a 400 by 400 array of ones and zeros, and we flatten that using the colon operator and convert it to string using num2string. And then we can take this whole array and say, like, oh, we want to replace the second column with the whole column of the flattened image. And that's how that works. It'll just be the reverse thing. It's like you just get your encrypted data, do the same thing, convert it to binary and a string, and then you look at the second column and you extract that out and make a copy of it and then reshape it.
So I'm going to go through and tell you about all the reach features we have implemented into this GUI. Beyond the fact that we have audio recording capabilities, we also have a bunch of error messages that'll pop up if you don't do things in the right order instead of the GUI crashing. So to start off, let's try to save an encrypted image. It'll tell us that there's nothing to save, that we need to encrypt an image. So if we try to encrypt an image, well, then we need to have a normal and hidden image loaded to be able to encrypt anything. If we try to recover an encrypted image, it's going to say that the algorithm hasn't been applied, and it'll say that for each individual algorithm. And so also if we try to encrypt a audio clip, we need to record an audio clip first and foremost. So if we let that start recording, then notice that after it's recorded, if we try to encrypt something, we need to load a hidden image first. So if we load a hidden image, we have to make sure that it is a 400 by 400 grayscale or black and white image. If we try to do RGB or something not 400 by 400, it'll tell us to do otherwise. And this goes the same for the normal image, except for RGB. If we try to load a grayscale image, no, it needs to be 400 by 400 by 3. And then if we do actually load these correctly, and if we press cancel, it'll show a message saying that we need to select an image. And then if we actually do encrypt something right, and let's do something here, encrypt that, let's encrypt that, and bring that up. And then now we have actually reset buttons for the recovery, audio encryption, and image encryption panel. And then if we didn't want to press all of those individually and clear this, we could clear all of them at once.